Hello everyone. In this lesson, we are going to learn about the limits of some transcendental functions. Specifically, we will compute the limits of exponential, logarithmic, and trigonometric functions using table of values and graphs of the functions. But before that, let us define first transcendental functions. So transcendental functions are actually functions that cannot be expressed algebraically. So we have here some examples: exponential, logarithmic, and trigonometric functions. Now to start, let us first have the limit of an exponential function. So to illustrate that one, let's consider this one. Investigate the limit of e to the x. So we have the function e to the x, the natural exponential function, as x approaches 0. Now, we have discussed in our previous lessons that we can investigate the limit or the behavior of the function through table of values and the graph of the function. So in this case, let us try to look at the behavior of the function as x approaches 0 through table of values. So we will investigate the table of values for values close to 0 from the left and from the right. Okay, so I will be considering the values close to 0 from the left. So we have here negative 1, negative 0.5, negative 0.1, 0.01, negative 0.001. So our values of x here moves closer and closer to 0 from the left. And from that, evaluating the function at these values of x, we will have the values of f of x. We have 0.378, 0.607, 0.905, 0.990, 0.999. So as you can see here, as your x approaches 0 from the left, the values of the function approaches 1, right? So we can say that the limit of e to the x as x approaches 0 from the left is equal to 1. Okay? Now, how about from the right? So we will have these values, 1, 0.5, 0.1, 0.01, and 0.001. So as you can see, the values gets closer and closer to 0 from the right. Now, evaluating the function at these values of x, we will have 2.718, 1.649, 1.105, 1.010, and we have 1.001. So as you can see, as your x approaches 0 from the right, the values of the function approaches 1. So we can say that the limit of e to the x as x approaches 0 from the right is equal to 1. So from that, since the left hand limit and the right hand limit both exist and are both equal to 1, we can say that the limit of e to the x as x approaches 0 is equal to 1. And notice that if we are going to evaluate the function e to the x at x equal to 0, we will still get 1, right? So this one is just equal to e to the 0. Okay? Now, let's look at the graph of the function. So we have here the graph of f of x equal to e to the x. So as you can see there, as x approaches 0, the values of the function approaches this point here, and that is equal to 1. That's why the limit is equal to 1. And we can also see that the value of the function at x equal to 0 is also equal to 1, since there is no hole, gap, or breaks at x equal to 0. So there is no discontinuities here, right? So that's why the limit of e to the x as x approaches 0 is also equal to e to the 0, and that is equal to 1. Observe also that as your x approaches negative 2, so the limit of e to the x as x approaches negative 2 is equal to e to the negative 2, right? So we can see it here. and that is approximately equal to 0.135. You can also see as x approaches -1 here, the limit of e to the x as x approaches -1 is also equal to e to the -1, and that is approximately equal to 0.369. We also have as your x approaches 1, so we have this point here, and the limit is the same. So we have the limit of e to the x as x approaches 1 is equal to e to the power of 1. And that is approximately equal to 2.718. And we also have as your x approaches 2. So we have this point here. So the limit of e to the x as x approaches 2 is also equal to e squared, and that is approximately equal to 7.389. So therefore, from that, if we are given with the function e to the x, we can actually evaluate the limit by direct substitution because the limit of the function and the value of the function are the same. Okay, and because of that, we have this theorem. If f is an exponential function and c is a real number, which is in the domain of f, then the limit of f of x as x approaches c is equal to f of c. Therefore, so if we are given with an exponential function, any type of exponential function, in evaluating the limit, we can just do direct substitution. Example, evaluate the following limits. So we have limit of e to the x plus 1 as x approaches 2. So again, from this theorem, we can just do direct substitution and we have e raised to 2 plus 1. So we just substituted the value of c to your x, and here our c is 2. So we have e to the power of 2 plus 1, and that is equal to e cubed. And this will be our final answer. Now, how about this one? Limit of 3 times 2 raised to x minus 2 as x approaches 3. So again, this is an exponential function, so we can just do direct substitution. So we have 3 times 2 raised to 3 minus 2. And this is 3 times 2 raised to 1. And this is equal to 6. So we have that answer. And lastly, if we have this function, 2 to the x minus 2 minus 2x plus 1. So we will evaluate the limit as x approaches 1. So doing direct substitution, we will have 2. Then we have raised to 1 squared minus 2 times 1 plus 1. And this is equal to 2 raised to 0. And we have 1 because any number except 0 raised to 0 is equal to 1. Okay? So that is if your function is an exponential function. We can just do direct substitution in evaluating the limit of the function. Okay? Now, how about if we have a logarithmic function? So let's investigate the limit of logarithm of x as x approaches 1. So this is the common logarithm. So the base here is 10. So my imaginary base yan na 10. Okay? So let us try to investigate the table of values for values close to 1 from the left and for values close to 1 from the right. So values close to 1 from the left. So I consider the following values. We have 0, 0.5, so it moves closer and closer to 1, and that is from the left. 0.9, 0.99, 0.999. So evaluating the function at these values of x, we will have undefined because log of 0 does not exist, and that is undefined, right? Log of zero point 0.5, we have negative 0.301. Then we have negative 0.046, negative 0.004, and negative 0.0004. So as you can see here, as your x approaches 1 from the left, the values of the function approaches 0, right? So we can say that the limit of log of x as x approaches 1 from the left is equal to 0. Now, how about from the right? So I consider the following values: 2, 1.5, 1.1, 1.01, and 1.001. So evaluating the function, we will have 0.0301, 0.176, 0.041, 0.004, and 0.0004. So as you can see, as your x approaches 1 from the right, the values of the function approaches 0. So we can say that the limit of log of x as x approaches 1 from the right is also equal to 0. And from that, since both the left-hand limit and the right-hand limit exist and are equal to 0, we can say that the limit of log of x as x approaches 1 is equal to 0. And take note also that log of 1 is equal to 0. So this is just the same as log of 1. Now let's try to look at the graph of this function. So we have here the graph of f of x equal to log of x. So from this, as your x approaches 0, no, from approaches 1, the values of the function approaches 0, right? And that is the same as log of 1. So again, this is the same as log of 1. Observe also that the limit of log of x as x approaches 0.5 is the same as log of 0.5. We can see it here that the point is shaded, right? So 0.5 is included in the domain and the value is approximately equal to negative 0.301, right? So we have that one. We also have the limit of log of x as x approaches 2 is just the same with the value of the function at x equal to 2, and that is log of 2, and that is approximately equal to 0.301. Now, how about when your x approaches 0? What will be the limit of log of x as x approaches 0? So, x equal to 0 is somewhere here, right? Now take note, the limit only exists if both the left hand and the right hand limit exist and are equal. In this case, since there is no graph from the left of 0, therefore the left hand limit does not exist. So from that reason, we can say that the limit of log of x as x approaches 0 does not exist. And observe that log of 0 is undefined, right? So from that, we can just do direct substitution in this case if we are given with the function f of x equal to log of x. And actually, we have this theorem. If f is a logarithmic function and c is a real number which is in the domain of f, then the limit of f of x as x approaches c is equal to f of c. So therefore, if you are given with a logarithmic function, we can evaluate the limit of the function by just doing direct substitution. For example, evaluate the following limits. We have log of x with the base 2 as x approaches 8. So here, in evaluating the limit, we will just do direct substitution, and we can also use the properties that we have learned in your Gen Math, okay? Properties of logarithms to simply evaluate the given function. Okay, so we have limit of log of x as with the base 2 as x approaches 8. So we have log of 8 with the base 2. And take note 8 can be written as 2 cube, right? And take note that logarithm is just the exponent, right? So in that case, we will have log of 2 cube with the base 2. And this one is just equal to 3. If the base here is the same with this one, the answer is the exponent. Because again, the logarithm is just the exponent. Okay? Next, we have log of ln of 5x minus 8 as x approaches 2. Doing direct substitution, we will have ln of 5 times 2 minus 8. And this is just equal to ln of 10 minus 8 or just ln of 2. So we can have this one as our final answer. Now, for the last one, we have log of the limit of log of 2x plus log of x squared plus 5 minus log of x minus 2 as x approaches 5. So doing direct substitution, we will have log of 2 times 5 plus log of 5 squared plus 5 minus log of 5 minus 2. So from that, this will now be equal to log of 10 plus log of 25 plus 5 is 30 minus log of 3. Now, using the properties that we know about logarithms, um, log of 10 plus log of 30 can be written as log of 10 times 30 because we have this property log of x times y with the base a, suppose a, is just the same as log of x with the base a plus log of y with the base a, right? And we also have log of x over y with the base a is just the same as log of x with the base a minus log of y with the base a. So from that, I can rewrite this one as, so I will continue here. So we will have log of 10 times 30 minus log of 3. And since we have minus here, we can apply the second property here. So we have log of 10 times 30 over 3. And this is now equal to log of 300 over 3 is 100. And take note, there is an imaginary base 10 here, and 100 is equal to 10 squared. So the answer is 2, right? So that will be our final answer. So that's it for logarithmic function. So we can just do direct substitution in evaluating the limit of any logarithmic function. Now, how about for trigonometric function? So let us just consider the function sine x. So we will investigate the limit of sine x as x approaches 0. So we will have here values close to 0 from the left. So we have the values negative 1, negative 0.5, negative 0.1, negative 0.01, negative 0.001. So as you can see, there is no unit of measurement here. So it is automatically understood that the angles here are in radian measure. So if you are using your calculator in evaluating this function, make sure that your calculator is set to radian measure. So makikita nyo dyan sa calculator sa screen ninyo, the default setup is in degree measure. Makakakita kayo ng D in your calculator. So you need to change that one to R. So you can just click shift then mode and makikita nyo yung radian. Then click the number corresponding to radian. Okay, so that's it. Now, in this case, if we will try to evaluate the function at these values of x, so we have the following value, negative 0.841, negative 0.479, negative 0.09, negative 0.009, negative 0.0009. So as you can see, as your x approaches 0 from the left, the values of the function approaches 0. So the limit of sine x as x approaches 0 is equal to 0. And this is from the left. Okay, so left hand limit is equal to 0. Now, how about from the right? So we have 1, 0 0.5, 0 0.1, 0 0.01, and 0.001. Evaluating the function, we will have 0.841, 0.479, 0.09, 0.009, and 0.0009. So as you can see, the values of the function approaches 0. So the limit of sine x as x approaches 0 from the right is also equal to 0. So from that, we can say that the limit of sine x as x approaches 0 is equal to 0. And take note again, sine of 0 is equal to 0. Let us try to look at the graph first. In this case, as your x approaches 0, this is 0 here, the value of the function and the limit of the function are the same. That's why we have the limit of sine x as x approaches 0 is equal to sine of 0, and that is equal to 0, right? Now, let's try pi over 2 here. So the limit of sine x as x approaches pi over 2 is also the same as sine pi over 2, and that is equal to 1. If we have pi here, we have limit of sine x as x approaches pi is the same as sine pi, and that is equal to 0. So from that observation, we have this theorem. If f is a trigonometric function and c is a real number which is in the domain of f, then the limit of f of x as x approaches c is equal to f of c. So therefore, if you are given with any trigonometric function, we can just do direct substitution. For example, evaluate the limit of the following. First, limit of cosine x minus pi over 3 as x approaches pi. So we can just do direct substitution here. So we have cosine of pi minus pi over 3, and this is equal to cosine of, so this is 3 pi minus pi, so we have 2 pi over 3, right? So 2 pi over 3 is located at quadrant 2, and the value of the sign of cosine at quadrant 2 is negative, while the reference angle here is pi over 3, so cosine of pi over 3 is 1 half, so we have negative 1 half, right there. Next, we have limit of cosecant x plus pi over 2 as x approaches pi over 3. So we have cosecant um, pi over 3 plus pi over 2. So we will have cosecant of, so we have 5 pi over 6, right? And 5 pi over 6 is located again at quadrant 2. And cosecant is the reciprocal of sine. So we will have 1 over sine of 5 pi over 6. The sign of sine in quadrant 2 is positive, and our reference angle is pi over 6, and sine pi over 6 is equal to 1 half. So we will have 1 over 1 half, and this is equal to 2. Okay? And for letter C, the limit of tangent of x minus pi over 3 as x approaches 5 pi over 6, we will have tangent of
5 pi over 6 minus pi over 3. So this will now be equal to tangent of, so we have 3 pi over 6, or just tangent of pi over 2. Tangent is equal to sine over cosine. So we have sine pi over 2 over cosine of pi over 2. Sine pi over 2 is 1, while cosine pi over 2 is 0. This is undefined. So therefore, we can say that the limit of tangent of x minus pi over 3 as x approaches 5 pi over 6 does not exist. So that will be our final answer. So again, to generalize, if you are given with an exponential, logarithmic, or a trigonometric function, and c is a real number which is in the domain of f, then the limit of f of x as x approaches c is equal to f of c. So therefore, we can just do direct substitution for these types of function in evaluating the limit. Okay? So that ends our lesson for this video. Thank you for watching, and I hope you have learned something.